Okay, I think we'll get started. If you're coming from the GNL project, I encourage you to look at the first video of this series to see if this is the right course for you. Well, we're going to extend our discussion of energy here now to include the concept of power. Power is simply how that energy is delivered over a period of time. So we might have 10 joules of output of some machine or something like that, and whether that 10 joules comes in 1 second or if that 10 joules comes in an hour, it's still just 10 joules. But there's a very different experience for that machine. To deliver the amount of energy rapidly is different than delivering it over a period of time. And so the concept of how fast that energy can be delivered is an important one, and that's what we call power. So power is the energy per time. We can think of that in terms of work, because work is an energy, and oftentimes when we're talking about power, we're interested in either a machine or an athlete or something like that. So what is the work per second? The units of power are called the watt, and it's a joule per second, or energy per joule per second here in SI units. So energy per time, joule per second. We can, what about force? We can do this in terms of force, but we have to be a little careful here. Power is a scalar. It is not a vector. So when we're talking about the force here, we do not have a vector quantity. While this is a vector, this is also a vector. So together, we don't talk about it here in this course, but it's the dot product which would produce a scalar. So it doesn't change power from a scalar to a vector using force. We just use the magnitude and the magnitude here of x. So work, what is work here? Work is force over a distance, and then we divide by time, and now we can isolate these guys to get a speed. So we have a force times the magnitude of the force times the speed will give us the power output. Okay, let's look at an example here of accelerating a mass. So we're gonna get a mass going. We're gonna push a mass going, accelerating it from rest to 5 meters per second, and then we'll let it go. So we're just gonna push it till we get it to 5 meters per second, and let's say we do that over 0.75 seconds. So obviously that wouldn't be us. Some kind of machine is pushing this mass. Okay, so how do we do this? Well, let's use energy, and we'll figure out the change in kinetic energy. We have no change in potential energy here. We're just moving across horizontally. So no change in energy. The amount of total energy going in will be the kinetic energy. And so we'll have 1/2 mass mv squared. Sorry, I think this is still right. So this, so we get 187 joules, and then we delivered that over 0.75 seconds. So that's 250 watts. All right, let's look at another example. Let's say we're pulling a sled across the ground, but now we have friction here. So we're going to pull the sled at a constant velocity, and the sled will be sliding on some ground with a coefficient of kinetic friction. I should have a K here. Coefficient of kinetic friction of 0.366. Let's draw the free body diagram for this box. So the normal force and weight force exactly counter, because we're just on this flat ground. There's a tension in the rope that's going to pull the box this way, and then there's an opposing force from the friction that's keeping us going at uniform motion rather than accelerating. The magnitude of the tension and the friction then must be equal and opposite, because we need this free body diagram to add to 0 vectorially. We can write our expression for friction. So this is mu times n. N is given to us by the weight here, because it's exactly equal but opposite the weight. So we have mg times mu, and so we get a total of 179 newtons. That's the force we need to keep this box moving and not slowing down. So the power, let's use this formula. Power is the magnitude of the force times the speed. So we take 179 times 3, and we get 538 watts. Okay, the last thing I want to talk about is power density. And this is what we refer to as specific power. It's got this weird symbol here. This lowercase p with a slash through it is one symbol for it. This is power per mass, and this is important in a number of places, but one place it's really important is in battery technology. How much power can this battery deliver, say for an electric vehicle, per kilogram of mass of that battery? And so that's something that engineers look at very carefully. Is yes, maybe we can deliver a lot of power, but the mass is prohibitive for a vehicle. Another place that it's really important is in the area of professional cycling. So the single, I believe the single most important metric for an athlete and judging whether they'll be successful as a professional tour cyclist is their power. Their power per body per weight, so their watt output on the bicycle per kilogram. And so the best professional cyclists in the world have a very high power or watts per kilogram output compared to their competitors. And then the last thing I want to talk about here is this thing called a watt hour. And we see this a lot in the big energy sector. We see it a lot in battery technology. And what in the world is it? You might be thinking, well, it's an energy per time, which it surely is, times the time. So it's just energy. And it is. It's a unit of energy. It's a measure of energy. It's not really an SI unit, although we could certainly turn it into joules very quickly. It's because this is a joule per second, and then we have hour here. And it's just a matter of convenience. We have just in our life's experience a better sense of the wattage of pieces of equipment. And so to think about using a 100 watt light bulb or a 500 watt device that's running for an hour, that would be like a 500 watt hour amount of energy needed. So for example, let's say we had this battery pack that could supply 20,000 watt hours before it stored 20,000 watt hours of energy that it could deliver then as needed. And we're in a small camper that is consuming on average 5,000 watts during maybe the evening period of cooking and keeping stuff cold and all that. Then we could take 20,000 divide by 5, and we would get an estimate of, you'd have about 4 hours of that kind of activity that you could do with this battery pack. And so I just wanted to bring this up. It's not an SI unit. It's not something that's in the book here, but it's something we see a lot in the context of power discussions.